Okay, I'm going to start sharing screen now. Okay, here we go. Okay, so the last time we stopped at question 16. Today we are going to go on to question 17, okay? This is the Kranji paper. So get the Kranji paper out and hopefully you've done it. If you have not, it's okay. Well, not okay, but just follow along and try to keep up as we go through the paper, okay? Okay, so question 17. The diagram shows the circuit for a hair dryer. So this is the motor fan for the hair dryer. And this is the heater, right? So it blows the hot air out. But all this doesn't really matter, okay? So what does matter is that the fan motor has a rating of 0.1 kilowatt, and each of these heaters have a rating of 0.4 kilowatt. What is the cost of running the hair dryer for 2 hours with switches P and Q closed and switch R open? So let's go ahead and close switch P and close switch Q. Switch R is left open. Okay, so we are not going to consider this heater because it's not going to be used at all anyway. So we are just going to consider the fan motor, which is rated at 0.1 kilowatts. And we are only going to consider one heater, which is rated at 0.4 kilowatts. Okay, so this is a question on how to calculate the cost of electricity. So step number one, I have to first come up with how much energy is used in terms of kilowatt hour. Okay, so step number one, we got to first calculate how much is the total kilowatt hour used. So we have this fella and we have this fella. So the total is total power is 0.1 plus 0.4, which gives me 0.5 kilowatts. But this is power. We still haven't calculated energy in terms of kilowatt hour. So now we need to calculate the energy in terms of kilowatt hour. So 0.5 kilowatts times the total hours. Let's take a look. Is running for 2 hours. Okay, so I need to multiply this by 2 hours, and it gives me 1 kilowatt hour. The cost of electricity is 8 cents every kilowatt hour. So if I only use 1 kilowatt hour, the cost is just 1 times 8 cents. And that gives me a total of just 8 cents. So the answer is D. Okay? Any questions? Okay, I'll take that as a no. Okay, no one raising hands. All right, let's move on then. Okay, question 18. Jack, you just entered, Jack. Jack. Jack, can you unmute yourself? I need a response from you, Jack. Jack, did you forward the meeting codes to Ethan and Teja?
I did already.
All right, thank you. Okay, so let's move on to question 18. Okay, so now I've got wires inside a cable. So this is the insulation, right? And inside is the actual wires here. But unfortunately, right, the wires, the internal wires are touching over here. So there is contact here, all right? So what is going to happen is that the current coming in, sees a short circuit over here. It does not want to go there because by nature, current is lazy. It always takes the easiest path. So if it doesn't need to go over here and do whatever it needs to do, power up the appliance, right? It will not go there. Instead, it will take the short circuit and go back this path, okay? So this is what's happening. There's a short circuit there. So what could happen? An appliance plug into a different socket could become switched on? Not really. The hairdryer plug into the socket could be damaged. The hairdryer plug into the socket could be damaged. Maybe. Let's KIV this answer. Could be. A person near the hairdryer could get an electric shock. No. Charges don't travel through air unless the potential between the 2 points are very, very high. In this case, it's not very high. The circuit breaker could trip. Yes, in this case, I think this is the more correct answer than this, because when a short circuit occurs, what happens is that the current increases exponentially, okay, when a short circuit occurs. So let me write this down. This is what is called a short circuit. Okay, this is what's called a short circuit. And when a short circuit occurs, the current shoots up. And when the current shoots up, the circuit breaker trips. Okay? So therefore, the answer is D. Any questions for question 18? No. Okay, so at any one point in time, if you are not sure, or if I'm talking too fast, or something I said sounded wrong, please just unmute yourself and say something, okay? Because I'm not seeing anybody's face, and you're all on silent, which is good, but that means I don't get any feedback. So if there's something that needs to be said, please say something, okay? Unmute yourself, say something. Okay, let's go on to question 19. So there's a question of magnetism. The trains are carefully removed from the magnet. What happens to the nails? Okay, as we all know, this is magnetic induction. And magnetic induction is a temporary magnet. So it is a temporary magnet, okay? Whether it is steel or whether it is iron, it is a temporary magnet, all right? So some of you will be saying, but steel is a hard magnetic material, okay? So this is a hard magnetic material. And iron is a soft magnetic material. So some of you will be saying that a steel will retain its magnetism more. Yes, but in this case, it's they are magnetized through magnetic induction, which is by nature a temporary magnet. Okay, so even if you have steel, it's just going to be a temporary magnet. All right. So once you remove this train, and once you remove this train, it will eventually lose its magnetism. And I'm going to say that both trains will fall apart. Okay, the answer should be A. Question? No question. Okay. Let's go on to question 20 then. Okay, so this is going to employ Fleming's left-hand rule. So I have a wire XY, okay, it's lying between two poles of a magnet. The ends of a wire are connected to a battery. In which direction will this wire XY move? So first of all, I have to know that this is a positive, this is a negative terminal of the battery. Current flows from positive, okay, to the negative. So I'm just concerned about XY, so I'm just going to follow the current direction. Current direction comes here. All right, so now I have the necessary information in order to employ Fleming's left-hand rule. Okay, this here. So if you remember, Manchester Football Club. Okay, so Manchester Football Club stands for motion. My thumb is motion. Feel, middle finger, current. So obviously, I can't impose my finger on the screen share. But what I'm going to do is that always remember the feel, right? Your index finger always points into the S. Okay, so I'm going to do that here. And my middle finger is going to go into the direction of the current. So current is going from Y to X, so like this. And my thumb is pointing up. Okay, so since my thumb is pointing up, it's going to be A. Okay, upwards. So the answer is A for question 20. Okay, any questions? No? Okay, let's move on then. Okay, so we are going to do paper 2 now. Okay, so for paper 2, this shows a velocity time graph. So first of all, you have to understand the graph. Okay, you have to understand the graph. This means that the speed is increasing. The velocity is constant. Okay, it's not changing its speed. And then it is slowing down. Okay, it's slowing down, it's slowing down, it's slowing down. At this point in time, when there's a negative velocity, what it means is that it's going in the opposite direction. Okay, so it's speeding up in the opposite direction and then slowing down in the opposite direction until it comes to a stop again over here. So this is what this graph means, okay? Okay, so what is meant by acceleration? They are basically asking you for the definition of acceleration. Okay, so acceleration is the rate of change of velocity. So you just got to remember this. Okay, I'm going to write this down. Acceleration is the rate of change of velocity. Okay. Next, calculate the acceleration of the car from 0 to 10. So I'm just going to concentrate on this area over here. Okay, 0 to 10 seconds. So first of all, write down the formula. Acceleration equals to V minus U over T. Okay. If you remember, V is the final velocity. So it starts here, it ends here. The final is 60. The final is 60. Initially, it was at 0. Initially, it was at 0. And the time taken is from 0 to 10. So that's going to be 60 over 10. And this gives me 6 meters per second square. Okay, so write down 6 meters per second square. All right, so remember this formula here. Okay, first of all, you have to remember this formula. Second of all, know what each individual symbol stands for. V is final velocity, U is initial velocity, T is time in seconds. Okay, so you got to remember all that. Calculate the total distance traveled by the car from 0 all the way to 55 seconds over here. Okay, so first of all, you got to know that to find the total distance from a speed time graph over here, you'll need to find the area under the graph. Okay, so area under the graph. So couple of ways you can do it. I'm going to break it up into this shape, and I'm going to break it up into this shape. So I'm going to find 2 areas, all right? So I'm going to find this shape plus the triangle. Okay, so the formula for this shape is half times sum of parallel sides times height, half times sum of parallel sides. So this fella is 0 to 30. So this is 30 plus this is 5. All right, this is 5 over here. Okay, times the height. So the height is 60. 60. Right? And I have to add the area of the shape here, which is a triangle, which is half times base. So base is 30 to 55. So that is 25. Okay? Times the height. The height is 40. 0 to 40. So some of you will be saying, hey, wait, hang on, hold up, sir. There is a negative 40 here. Do we need to consider the negative? In this case, no, because if you are looking at just total distance, we are not looking at displacement. We are looking at distance. So if you remember, the difference between displacement and distance is that distance does not care about the direction. Okay? Remember, this distance does not care about direction. So if I calculate this fella moving forward, so the car has moved forward before stopping and then moving backwards over here like this, what I need to calculate is the distance move forwards and the distance move backwards. Okay, so I need to calculate this plus this total distance. All right. I'm not talking about displacement. If I'm talking about displacement, then yes, I have to consider the negative sign, and therefore, let me change to a different color. Displacement would be this. Okay, so this would be your displacement. All right, over here. This is your displacement. I hope I haven't confused you. Okay, so if you don't really understand this whole displacement thing from this graph, it is okay. It is all right. Just know that we are calculating distance here. Okay, so distance is area under the graph over here plus over here. Okay, so which is what we have here. So let me press my calculator. You should get an answer 1550 meters. Okay. Okay. Any questions for question 1 of paper 2? Okay, no one is raising hands. We are good. Okay. Let's go on to question 2. Sorry, there's a part D, my bad. Okay, so by considering the forward force and the resistive force, explain why the speed remains constant between 10 and 15 seconds. So between 10 and 15 seconds, the speed is constant. Okay, so you have to remember this. Logic. Whenever you have a constant speed, what this means immediately is that you have to know that there is zero acceleration. And when you have zero acceleration, it means that the resultant force is 0 Newton. Okay, so you have to follow this argument whenever you see constant speed. Speed is constant. Whenever you see speed is constant, you have to follow this argument. All right. So what this means is that if this is the car, this is the forward force, and this is the resistive force, can be air resistance and so on and so forth. Okay, what this means is that this fella and this fella must be the same. Okay, so let's make that argument in words here. Okay, when the speed is constant, since speed is constant, this means that the resultant force is 0 Newton. Okay, therefore the forward force and the resistive forces are equal. Okay, Ken? So keywords, the keywords, you have to tell me that the resultant force is 0, forward and resistive force are equal. Okay, Ken? So follow this argument whenever you see constant speed. Every time you see constant speed, always underline it because constant speed usually means something. Okay, so underline it. And once you underline it, always bear in mind this logical step here. Okay. Okay, so that was question 1 of paper 2. Unfortunately, I can't show you the working for question 2. Simply because I need to show you using a ruler. And there's no ruler function with the Microsoft Edge that I'm using to show you with the annotation, right? Does anyone need me to explain how to go about solving question 2? Can you just raise your hand if you need me to explain? Okay, I don't see a hand raised, so I'm going to assume that it is all good. Okay, I'll give a wait time of another 5 seconds.
So this is the one where you draw the parallelogram, right?
Yes, exactly. You have to use a scale, draw a scale drawing of a parallelogram. Okay, so since no one is raising your hand, I'm going to assume that you all know what to do. Let's go on to question 3 now, okay? Okay, so water is going to be funneled into a pipe, okay? So there's the water flowing down. It's going to flow down a pipe, which is 150 meters tall, and it's going to be directed to a turbine over here. Okay, a turbine is something that spins very, very fast, either due to wind or either due to water in this case, all right? So each second, 250 meter cubes of water is funneled down the shaft. The density of water is 1000 kg per meter cube. What is the mass of water that enters the turbine each second? Okay, so I'm going to assume that the mass of the water entering down this pipe or this shaft is going to be the same mass that enters the turbine. Okay, I'm going to assume that everything is constant here. Okay, so formula to use, density equals the mass over volume. Okay, this is the very basic formula that you need to know. So please go and remember this formula. Okay, density of water is 1000. So let's write down 1000. Mass is what I want to find. And the volume is 250 meter cube. So this is 250 meters. All right. Mass is therefore 250 times 1000. So this is 250,000 kg. Okay. Next, what is the loss of GPE when it falls through this vertical height? What is the loss? Basically, I employ this formula, GPE equals to mgh. You have to know and remember this formula, okay? So we calculated the mass earlier to be 250,000. G on Earth is 10. Okay, I'm going to assume that we're on Earth. And the height is 150 meters. So this will get you 375 million joules of energy. Okay, so this is 375. If you want to, you can use prefixes if you want to. Megajoules, or if you want to, you can just write it in the whole number. That is fine as well. Okay. All right. Let's go on to part C. Calculate the speed at which the mass of water reaches the turbine. So what's going to happen is that there's going to be the energy loss here, right? The energy loss falling down the pipe. So the energy loss here, which was 375 megajoules, all this energy loss from GPE is not going to disappear. It's not going to be vanished. Instead, all the GPE that is lost, all this 375 million joules, is going to be converted to kinetic energy. And I'm going to assume that all this kinetic energy, as it flows into the turbine, all this KE is going to be equals to the 375 million joules. Okay, I'm going to assume that there's no energy loss here along this journey over here. Okay, so assuming that there's no energy loss over here, so all the 375 million joules converted to KE is going to stay as 375 million joules as it enters here. Okay, so from there, if I know that the GPE loss from falling is going to change into the kinetic energy of water going into the turbine. Okay, so this is a statement to show the marker that I know where the energy change took place. I can write down next that this is equals to 375 million, and this KE is half mv square. Okay, so the mass is from part A, this one, the 250,000, okay, over here. So I'm going to put that in. I'm going to press my calculator, and you should end up with V of 54.8 meters per second. Okay. So I already stated the assumption that I made just now is that as it falls, right? As it falls and as the water travels to the turbine, no energy is going to be lost. But we all know that that's not going to be true. A lot of the energy is going to be lost as sound energy. This is a very, very noisy operation. So in reality, a lot of energy is going to be lost here, primarily through sound, through friction, so on and so forth. Yeah, but theoretically, for our calculation, we are going to assume, no energy is lost to the surroundings. Okay. Any question for question 3? Okay, I don't see any hands going up. I'll give you another 3 to 5 more seconds. Think whether you have any questions. Okay, if not, let's go on to question 4. Okay, question 4. This is a man with a wheeled bag. The mass of the bag is 50 kg, all right? So they want me, part A, draw an arrow to indicate the action of the weight of the bag. So the weight usually comes from the center of gravity, yeah, because that's where all the weight of the object appears to act on. So they very nicely provided the center of gravity over here. And to draw the line of action, it is always vertically downwards over here. Okay, with an arrow, and of course, label it as weight. Okay. So to prevent this trolley bag from falling over, the man has to hold it here and provide an upward force. All right. So this is a question on moments. The weight is going to create a clockwise moment. So this is going to be a clockwise moment. Whereas the man holding on to the handle over here, this is going to create a anti-clockwise moment. All right, so with that in mind, and the wheel being the pivot, we can start calculating the unknown upward force. So first of all, always write down the statement, due to principle of moments. All right, write that down. Sum of clockwise moment equals to the sum of anti-clockwise moment. Okay, so this is something like your formula. So please write this down. Every time you do a moment question where you need to employ the principle of moments, write this down. All right. Next, let's calculate the clockwise moment. Okay, let's calculate the clockwise moment. So the moment is always the force times the perpendicular distance. Okay, remember that it's always force times perpendicular distance. So same thing for the anti-clockwise moment. It is always the force times the perpendicular distance, right? So the force downwards for the weight is not 50 kg. It is not 50 kg, that's the mass. I have to calculate 50 kg into Newton. So assuming that we are on Earth, that is times 10. Okay, so 50 kg, I times 10 is 500 Newton. So that is the weight. So that's 500 Newton. The distance is 12 cm, all right? It is the distance, the perpendicular distance from the pivot to the line of action over here, okay? So I'm going to leave it as 12 cm. Now, some of you are going to say, whoa, 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 hold up. You told us that in class, it is always Newton times meters. And yes, if you want to be absolutely technically right about it, convert this to meters. But in this case, I'm going to leave this as cm because I'm going to leave the next distance in cm as well. So the cm and the cm on both sides of the equation are going to cancel off anyway. Okay, so I'm just going to leave it as cm. If you want to convert it to meters, please, by all means, go ahead, right? So the upward force here is the unknown. I don't know what it is. I'm just going to leave it as F2, all right? The perpendicular distance over here is 60 cm. Okay, and finally, you press your calculator. The unknown upward force should be 100 Newton, if the calculations are correct. Okay. Now, when the man lets go of the handle, okay, when the man lets go of the handle, the bag will fall down. I think by common sense, we know that is going to happen, right? We know that's going to happen, but why? Okay. So before I write down the answer, what we have done is that we have taken away the anti-clockwise moment provided by the man. So now we are only left with the clockwise moment. Okay, we are only left with the clockwise moment. So we have to kind of explain that in our answer. Okay, so step number one, state that the anti-clockwise moment is removed, and since the line of action due to the weight of the bag produces a clockwise moment. Okay. The bag falls in a clockwise direction. Okay, so keywords you must include line of action produces a clockwise moment. Okay, therefore the bag falls in a clockwise direction. All right. Are we good? Okay, any questions for question 4? If you do, just speak up or raise your hand.
What is line of action?
Okay, so a line of action is a diagram showing it's a okay, it's a line showing you the direction of the force. Okay, so if I have a box, this is the center of gravity. And if I want to show what is the weight and how is the weight acting, I draw a line of action. Okay, so it doesn't always need to be it doesn't always need to be from the center of the object, because if I got an irregular object, let's say I got an irregular object, it's not going to be in the center here, right? It's probably going to be somewhere here. The line of action, if we are on Earth, right, is always going to be a vertical line pointing downwards. Okay, so and the line of action is always from the center of gravity. So even if, let's say, I move this box this way, the line of action, which is still at the center, is not going to be like that. This is wrong. Okay, this is wrong, because I told you that the line of action is always going to be vertical because of gravity. So it's always going to be, sorry, it's not very straight, but it's always going to be vertical, like so. Okay, so that's the line of action. It's a line you draw to show how the weight from the center of gravity looks like in a diagram. Hope I made that clear. Are there any other questions? No? Okay. I've been talking for close to 50 minutes, 50. I'm going to give you a short 5-minute break. Yeah. So if you need to use a toilet, if you need to go grab a glass of water, go ahead. The time now is 8:57. I will start at 9:02 again. Okay, so short 5 minutes break, toilet break, water break, or even just go walk around. I will start in 5 minutes time. All right. Okay, time now is 9:02. I hope everyone is back. Can I get just a thumbs up from everyone to make sure that everyone is back? Thank you, Ethan. Cool, Kashawn, Chiu, great. The rest of y'all, Jack, Dinanan, Stefan, Preston. Good, Preston, I saw your thumbs up. Thank you, Stefan. Thank you, Dinanan. Okay, let's go. All right. So let's move on to question 5, all right? So question 5 is testing you on the chapter of thermal properties. I've got a pure substance heated into a liquid, okay, from 30 all the way to 90 degrees. And this has a melting point of 60 degrees. So this is the melting point. Let me just put that down, melting point. It is from a solid to a liquid. So I know this starts off as a solid over here and ends up as a liquid over here, okay? Describe the differences between the particles at 40 degrees over here and at 80 degrees over here. okay? So this is 80 degrees. So basically what they're asking you is to talk about the differences in particle motion and particle arrangement between solid and liquid, okay? So you need to talk about two things. One, the motion, and two, the arrangement. Okay, so I know that solids, it is vibrating in place, right? Because they are stuck in a fixed position. So the motion of the particles is that it's vibrating in place. Whereas liquid, the particles kind of slide past each other. Okay, so that is the motion. Arrangement, they are closely packed, orderly for solids, and for liquids, they are still closely packed, right? Liquid particles are still closely packed, but they don't have a fixed arrangement, so in a disorderly arrangement, okay? So let's write all that down. Let's mention the keywords. Okay, so at 40 degrees Celsius, it is a solid, okay? Therefore, the particles vibrate about a fixed position, but at 80 degrees, it is a liquid, and particles slide past one another. Okay, so I've talked about the motion. Next, we have to talk about the differences in arrangements, right? So in a solid, particles are closely packed in a orderly arrangement, but in a liquid, particles are disorderly. Okay? Disorderly arranged. Not sure whether this is an oxymoron, but it is disorderly arranged. Okay? Right? Okay, next, part B. Part B says, at XY, the thermal energy gained by the substance did not bring about a change in temperature. So the thermal energy gained by the substance is used to break the intermolecular bonds, right? But that's not the only thing. You also have to talk about the kinetic energy not rising, okay? Because kinetic energy is correlated to the temperature. So if the temperature doesn't rise, the kinetic energy does not change as well. Okay, so you got to talk about two things. The first thing is okay, so even though they didn't state here, right? They just use the word thermal energy. If you remember when I taught you this chapter, I also taught you this keyword called latent heat. Yeah. So every time there's a change in state, it is absorbing latent heat. So I'm going to use a latent heat here as a keyword as well. All right. So the thermal energy is absorbed as latent heat. Okay. And this is used to break intermolecular bonds. Okay, so that's the first part I was talking about. Now the second part is, and the Ke doesn't change. Therefore, the temperature stays constant. Okay, so I'm going to underline for you once more the keywords. Bring in latent heat. Every time there's a change in state, bring in latent heat. Okay, it's used to break intermolecular bonds, or you can also say used to overcome the forces of attraction between the molecules. And the next thing is you have to talk about the Ke staying constant or the Ke not changing. Okay. So every time I notice that every time there is explain or every time there is a describe, you guys lose quite a few marks. It's not that you don't understand the concept, it's that you don't put in the keywords. So as I'm going through these papers as revision, right, I will always make it a point to highlight the keywords. So make sure every time you study, you use the appropriate keywords. Okay? Okay, next. Now we are going to talk about heat transfer, right? Okay, so how does a heating element heat up all the water in the kettle? So by now you should know that this occurs because of convection. So I need to see this keyword, convection current. Okay, so I need to see this keyword, convection current. But to expand on the concept of convection, you need to start from the beginning. So you need to say that the heat causes the volume of water to expand. Okay, so I need to see this argument. Every time you talk about convection because something is heated, right? You have to say that, okay, so let me write this down over here. You have to say that the volume of is either liquid or water or gas or whatever it is. I'm just going to write down fluid here. Increases as it is heated. Okay, so I got to see this, the volume of whatever it is increases. Okay, so that's step one. Step two, therefore, the density decreases. Okay, so bring in density as well. The third argument is that, therefore, the hot, I'm going to write down a generic fluid. So if you want to write gas, you want to write water, you want to write whatever that fluid substance is, rises, and the cold fluid sinks. All right. And lastly, therefore, a convection current is set up. Okay, so every time you answer a question on how a fluid is heated up and so on and so forth, always talk about volume increasing, density decreases, hot fluid rises, cold fluid sinks because of the difference in density, and therefore the convection current is set up. So it must always go in this flow. Remember that these are the keywords for this answer here. Okay, I'm not going to write it down in full. I'm just going to provide you the keywords. Just patch it up to make it grammatically correct. Okay. Okay. Next, white plastic. So there are two things over here going on. There's white color and there's plastic. Okay. So they're saying that white plastic prevents heat loss. Okay, it reduces heat loss. So how does it prevent heat loss? So two things. I'm going to talk about the plastic first. Okay, plastic is a bad conductor of heat. Okay, so you have to say that plastic is a bad conductor of heat. Therefore, heat loss is reduced via conduction. Okay, so this is how plastic prevents heat loss because it is a bad conductor of heat. Now I'm going to talk about the color white. So now I'm going to talk about the color white. Okay, white is a bad emitter of, and this is the keyword, blank heat. Okay, starts with an R. So let's ask Preston. Preston, can you help everyone out here? What is this keyword? White is a bad emitter of what heat? Starts with an R. Do you have any idea?
Wait. What's the keyword?
Yeah.
Radiant.
Very good. Okay, this is the keyword, radiant heat. Okay, when you talk about colors being a bad or good emitter or absorber or whatnot, the keyword is always radiant heat. And some of you get confused. Sometimes I won't be surprised if some of you say that, oh, white is a bad absorber of radiant heat. But in this case, we're not talking about it trying to absorb energy, right? In this case, we're talking about it preventing the energy from being lost. So it's a bad emitter of radiant heat. Okay, therefore, loss, no wait, let me change it grammatically. Therefore, heat loss via radiation is reduced. Okay, so keywords here. Bad conductor, plastic is a bad conductor, and white is a bad emitter of radiant heat. So these are the keywords that you have to take note of. Okay. Okay, I think I can go through one more question before I end today's session. Very quickly, yeah. Okay, this is vibration, and then waves are formed. Wavefront. So I believe I included the answer with you with this. So you have to know that wavefront is an imaginary line joining all the points of particles in the same phase. So this one you just have to remember it. Okay. Okay, so two corks, A and B, are floating. The distance between successive wavefront is 8 cm. So I know from here to here is 8 cm. Locate the possible positions P, Q, R, or S. P, Q, R, or S. As shown in figure 2, that A and B are positioned at that point. Let's see. Oh, okay. So this is cork A, this is cork B. So one appears to be on the wavefront itself, right? One appears to be on the wavefront itself, and the other is in between two wavefronts, okay? So it is P. I would say this is P. And this middle part is over here, R. Okay? Can? So it is P and R. Because from here to here is one wavelength. So it's from here to here. This is one wavelength. So if cork B is in between the wavelengths, it must be at R. All right? Can? So cork A, I would say it is at P, and cork B, I would say it is at R. Okay? Calculate the speed of the wave. Calculate the speed of the wave. So it's V equals to F lambda. Remember this formula over here. V equals to F lambda. The frequency is the time taken. Frequency is how many waves there are in 1 second. Okay. In 1 second, this is 1 second. Over here, I have 1, 2 waves. So the frequency is 1, 2 waves in 1 second. So I've got 2 hertz. The wavelength, they said it is 8 cm. So you have a choice here. What you can do is you can leave it in cm, and this gives me 16 cm per second. All right, you can do that. Or if you want to be totally technical about it, technically right about it, you can change it to meters, which is 2. Change it to meters divided by 100. You get 0.16 meters per second. Okay, I believe both answers will be accepted. Okay. Okay, next. When it enters a deeper region, so when it enters a deeper region, okay, the wave travels faster and the wavelengths will be longer. Okay, so the wavelengths will be longer and the wave travels faster. So two things will happen. Speed increases, wavelength increases. Okay, and why? Because frequency stays the same. And if I'm using the formula V equals to F lambda, if this is the same, wavelength increases means the left-hand side of the equation must also increase to make sure that both sides are equal. Okay, so essentially that's the argument that you have to make over here. State what's happening, Why? Because there's an explain. Why? Use this formula to explain the why. All right. Any questions for question 7? Any problems? No? Okay. So the time now is 9:25. I'm going to end the lesson here. I'm going to give you 5 minutes to prepare for your next lesson. I don't know what lesson that is. I think Ms. Jo will be conducting a lesson. So I'm going to give you 5 minutes to log off here, prep for your next lesson, and complete the rest of this stack of prelim papers. I'll be going through with you this stack when school reopens. Okay? Any last questions before I close this meeting? If not, can I see a thumbs up before you log off? Okay, thank you, Ethan. You can log off. Thank you, Kashawn. You can log off. Yes, Preston.
Wait, what? It's not Preston, it's me.
Oh, yes, Denanan.
We still about motion, right, for question 5.
Okay, for the rest of you, if you have no questions, you can log off, all right? Denanan, question 5.
A.
5A, yes.
Can you talk about attractive forces for motion?
No. Motion is talking about how they move.
Yeah. And when do we talk about the attractive forces?
You can talk about it to explain. You can talk about it to explain why they move this way.
Oh. Okay, then bye.
Okay, I'll see you later. Okay, bye, Denanan. Stefan, Clayton, any issues? If there are no issues, I'm going to remove you now, okay? Clayton and Stefan, I have a next class starting in 5 minutes, all right?